Hello, dear students. I welcome you again in this lecture series on modern physics. And so far, so good. Remember that we are doing module 1 of our syllabus, and that module 1 is about electrodynamics. First, we tried to build up the mathematical foundations, which are very important to understand the theory of electromagnetism. Then I, of course, in my previous lecture went through all the experimentation from which we deduced empirical laws and were trying to understand the problems related to electricity and magnetism. Right. And today's lecture is extremely important because we are going to dig into the heart of electromagnetism. We are going to develop a theory which would not only unify electricity and magnetism, but it will contain optics as a byproduct. So this is the theory of Maxwell's equations, and this is actually the structure of Maxwell's equations, and which is extremely important in modern physics. So I will get into Maxwell's equations before going there, and we would like to understand one of the fundamental properties of electric charge, which is charge conservation. That electric charge is conserved. You can only move it from one place to another place. There is no way to create a charge or destroy it. So let's get, first of all, try to understand this conservation principle in detail and then develop a mathematical flavor of this principle. And then we'll get into the Maxwell scheme. We'll develop the Maxwell's first equation, second equation, third, and the fourth equation is where the main focus will lie, because it's the fourth equation where the Maxwell's contribution comes into play. So let us get started, man. So therefore, let me dive into the conservation of charge. So what is conservation of charge? How do you understand that charge is conserved? What do we mean by conservation of charge? Naturally, you will say that, yeah, we have gone through this idea in upper high school where we learned that no charge can neither be destroyed nor created. That is what we mean by conservation of charge. I mean, that's what it is. That's right. But I can give an example where charge looks conserved but is not allowed by the conservation of charge rule. So you see, for example, I have a charged object. Let us take the simplest case. Let's not be that, no, take a charged object kind of thing. Let's take one charge, one unit of charge, which is the charge of an electron. Suppose I have one electron, right? At this place in this room, I have one electron. This is the electron. Suppose it's a purely hypothetical experiment. Okay, now you'll see, you have one electron. How do you control it? No, no, I will not fall into those arguments. A pure thought experiment. Try to first develop thought experiments, right? So suppose I have one electron here in this room, and what's its charge? It's one electron. Electron is itself the unit of charge, right? Electron charge, what you call as. So we'll say that, okay, one electron has one unit of electric charge, right? In the right set of units, in natural set of units, what you call as. Now, what happens is that, let's assume that this electron vanishes here. It's completely vanishing at this point of space and time. And at the same time, the moment it vanishes here is that at the same time it emerges, is created, say, on the moon. The moment it vanishes here in this room is the same moment when it was created in the moon. So again, the charge is conserved. I mean, the charge of the universe did not change. All you allowed is that the charge got switched off at one place, got completely destroyed at one place, and at the same moment emerged at somewhere else. So the charge remains still conserved. Now, this is where this conservation of charge comes into our our deeper understanding. That's where the deeper understanding of the conservation of charge lies. This way, conservation of charge is not allowed. That charge can vanish here, emerge there. That's not allowed, because that kind of conservation is called as global conservation. That you are not actually, the particle is not moving between the 2 points. So remember, what is the strict statement for the conservation of charge? It is that charge is conserved. You cannot create or destroy it. But at the same time, if there is a change in charge, if the charge changes at a particular place, then it has suddenly moved to some other place. So you can only move it from one place to another place. You have to move it, physically move it, right? It's not possible that it will vanish at one point and get created at another point and still conserving charge. That principle, that global principle, is not allowed. So how do we strictly say conservation of charge? We say charge can neither be created nor destroyed, and it can be only transferred from one point to another point. When you say it can be transferred from one point to another point, then you are referring to what's called as local conservation of charge. So charge is locally conserved, and the idea that charge is locally conserved, this is the powerful statement which I will use in deriving what's called as the conservation of charge equation or continuity equation. So remember this very important point, because that is what actually, that is the idea which I will use in defining the equation of continuity. And if I allow charge to be conserved like globally, then I cannot derive the equation of continuity. And this is the fundamental philosophy of this law. Remember, whenever you learn anything in physics, learn it at a deeper level, learn it in a more clearer way. Fine. So I will try my best to do that, and you have to enjoy it. Okay, come on. So let's do it. So assume that there is some region of space. This is the regions of volume V, whatever it is. So there is some bunch of charges there. So this is the charge sitting there, and in some, so I'm packing this charge in some volume, and that this charge may be more at some places, maybe less at some other places. So it has a profile defined by the charge density rho. Charge density rho defines the profile of this charge, how the charge is distributed within this volume. Fine. If I want to get the total charge, all I have to do is to integrate this rho over the whole volume. That's it. Now suppose that charge is now changing. How it is changing? It's moving. It's physically moving. The motion of charge, right? The charge going from one point to another point. The charge is moving. That is what current is. So current is nothing but the flow of the charge is current. So we define current that the charge is going somewhere. So but if the charge is moving from this region, is going away from this region, then the total charge within this volume is going to drop. The whole of the charge within this volume is going to drop because it is going out. It's going out. Therefore, the charge that I initially started with is dropping. So how much amount, the rate at which it is going out, if it is going out very fast, then the rate at which the charge is dropping is very large. Now question is, how do I calculate how much charge is going out? How do I calculate that? So for that, what I do is that I assume that there is a closed surface around this distribution, right, enclosing this volume, and the charge is flowing through this surface. Now this small surface is ds. Now how much charge is flowing through this surface per unit time? Now per unit area, I will say that the way charge is flowing, see here there will be more charges going through this region, maybe less charges going through this region. There will be, say again, some charges going through this region, some charges going through this region. So there will be a charge flow profile. That charge going through this surface has its own profile, right? And that how much charge is going at a particular through a particular surface would be defined by this what's called as current density. It's flow of charge going through a surface area, a certain surface per unit area is this charge density J. Current, the current flowing through the whole area, through this whole area. That will be total current flux. That will be linked with that how much charge is actually coming from the source, right? That suppose this is the initial charge distribution, how much this charge distribution is dropping, that will tell us how much flux is through this surface. So I won't write down it mathematically. How should I write it down? I will say that the charge that is leaving this region, right, so it is decreasing, so I write negative, is equal to the flux of the current passing through the surface and closing this region. Right, this is how you put it mathematically. It's nothing but simple, that conservation of charge written in a mathematical way. J will tell me how much current is flowing per unit area. Dot ds is through that area. Integration of that, see, J is current flowing per unit area. Dot ds is projection of that current through that area. Then integral is through the entire area. So entire area, you just sum up the entire current through the entire area. That gives you how much current is actually coming from the source, right? So the distribution of the charge here, the charge is going out, so how much it is leaking out would depend on how much flux of the current is going through this surface, and that how much is the flux of the current through the entire surface is given by this integral. So this is the flux of the current through the surface, and it is connected to the how locally the charge is coming out from the region that I considered initially. From the initial distribution, how much current is, how much charge is flowing out. So this comes from the fundamental definition of the current. Now we know that I can write this charge in terms of the distribution, that's in terms of the charge density, as rho dV. Rho is the density profile, the distribution of the charge, and dV is a small element, so that would give me small amount of charge. The entire charge would be the integral rho dV. Now push it back into that equation. If I substitute, I have minus d by dt. For very simple mathematical reasons, I take partial derivative of this q, that is rho dV. Partial derivative, you know, the fundamental meaning of partial derivative is that you keep other variables fixed, is equal to integral j dot ds. Right, so this is what I get. Now the problem here is that this is a volume integral, whereas this one is a surface integral. So I want to write down a differential equation. Therefore I should have same type of integrals on either side. Then I can compare integrands. So what I do is that I would like to convert this into volume integral. Do I have any recipe that converts this into volume integral? The answer is yes. We have the theorem of divergence, right? So let me rewrite what we have now. We have minus del by del t of integral rho dV equal to surface integral current density, the flux of the current density through that surface. That's what we have obtained by the definition of the conservation of charge, right? So now what was our problem? Our problem was that how to convert this into volume integral. For that, we know that there is what's called as divergence theorem. That is that if we take any vector field and take it as flux over a closed surface, right, is equal to the divergence of that field over the volume enclosing that surface. So use that same idea in this equation. So what do we get? Come on, what do we get? We get minus del by del t of, come on, rho dV is equal to, now we have divergence of j and dV. Or I can write it more specifically as integral del rho by del t dV equal to minus integral del dot j dV. Now we have the same integrals on either side, right? So integration is over the volume, same volume, and therefore the integrands must be equal. That means this fellow must be equal to this fellow with the negative sign. So therefore I write down that divergence of j is equal to minus del rho by del t, or divergence of the current density plus del rho by del t is equal to 0. Now this equation is nothing but, this is the conservation of charge. This equation is the equation for the conservation of charge. It tells me that the rate of change of charge, right, charge density, the rate at which the charge density changes, right, is equal to the divergence. It depends on if the charge density is changing with time, then surely the current density is spreading out, right? So the spreading out, that is the divergence of current density, is related with whether the charge density at a particular location is changing or not. So that means if the charge density is changing, so it's actually charge moving out, it is going away, it is going somewhere. So that's what we are saying, and that you cannot create a charge, but you can transfer it, you can move it, you can pass it from one point to another point, and that is contained in this equation. So this is the equation for the conservation of charge. So whenever I'm referring to the equation of conservation of charge, it means del dot J, the divergence of the current density is equal to the negative rate change, rate change of rate change of the charge density. So this is how the equation is proposed, right? So this equation we will now here onwards call as the law of the conservation of charge. So if I tell you that what is conservation of charge, how do you express it? You should say the divergence of the current densities plus the rate of change of the charge density is equal to 0. That's what the equation of continuity tells us, and this equation translates into the conservation of charge. So far so good. So now we have conservation of charge with us. For that we have a differential equation, and now we'll move down to Maxwell's first equation. So what is Maxwell's first equation? How do we derive it? So we recall our Gauss law. So we start with Gauss law. What was Gauss law? Gauss law was that, that flux of electric field through a closed surface is equal to charge enclosed in that surface divided by epsilon naught. This is what you learn even in upper high school. That what it tells me is that if there is charge somewhere and I have a closed surface, then the flux through that surface is given directly by the charge within the surface divided by the epsilon naught. Epsilon naught is called the permittivity of free space. What is that permittivity? What do we mean by permittivity? Permittivity is how it is actually resistance to the electric field offered by a medium. So that least resistance, how much a medium allows an electric field, and the least resistance to the electric field is offered by the vacuum itself. So that how much vacuum allows electric field lines to pass through it is contained in epsilon naught. Actually, epsilon naught is maximum for vacuum itself. So more value of epsilon would mean that less is the electric field allowed to propagate in that particular medium. So it gives a notion of how much a medium allows electric field to get through it, right? So keep that in mind just for your understanding purpose. So remember that. So this is our Gauss law. So what the Gauss law tells us that how much field goes through a surface depends on what is charged inside the surface, right? And that field, it should be allowed by the medium itself. And since we are now in vacuum, so we use epsilon naught. Now, what we can do is that this charge inside the surface, I can write it in terms of charge density. Suppose there is a charge profile inside the surface. So the entire idea of this charge can be put in the form of a distribution. So if I write it in terms of the distribution of charge, so then I can rewrite this charge enclosed as 1 by epsilon naught integral rho dV. This gives me how the charge is distributed within that volume that I'm choosing, right? So because flux is through the surface, so inside the surface there is some volume, and how is the charge distributed in that volume? That would be contained, that profile of charge, how charge is distributed within that volume is contained in the charge density, and I can write this total charge as integral of rho dV. Now again I have the same thing and that I had earlier, right? On this side you have a surface integral, or this side you have a volume integral. So again I will convert the surface integral to volume integral by using the divergence theorem. So if I put that divergence theorem here, so what do I get? So I get integral of del dot E dV over the volume V is equal to 1 by epsilon naught integral do rho dV. Now again, since the integral is over the same volume, and we have both same integrals on left hand side and right hand side, it makes only sense when the integrands are equal. So, and from that, what do we get? We will get, so if we match integrands, so it is divergence of the electric field. divergence of the electric field is equal to charge density divided by epsilon naught. This is the Maxwell's first equation. We also call it as Maxwell's first equation. So the Maxwell's first equation is nothing but it's a differential form of the Gauss law. You say, okay, Gauss law was already there. Why do I need this? Why do I need the differential form of the Gauss law? Right? If the Gauss law is already there, so why do I need a differential form of that law? The understanding is that Gauss law gives you something like, it gives a global understanding of electric field, electric flux because of a charge distribution. It connects charge distribution to a remote place, right? So I have a charge distribution here, and then I have a surface enclosing it. Then it tells me what is happening on the surface because of that distribution. It is not telling me the field which the distribution is created, how that field is varying from point to point. That information is not contained in the Gauss law. And this differential form of this law tells me exactly the entire profile of the field, how the field varies from point to point in space, and that I can get that field by solving this differential equation. The question is that, is it easy to solve this differential equation? What are the challenges of solving in this differential equation? It's not easy, by the way. The reason is that it's a partial differential equation, fine, and then it has a source term also. So you have two challenges. One, it has a source term. You need to know the source term, and then and only then you can actually start thinking about the solution of this equation. The other problem lies that this does not have a unique answer. It can have any answer, like it can have multiple answers, and that there will be multiple functions of E, mathematically function E as functions, which would satisfy this equation. But for a particular situation, we only have one unique solution. That's what in reality will make sense. So for that, you need to know boundary conditions. And so unless you don't supply boundary conditions, then you can't track down the solutions of this problem. And then how is it mathematically, even suppose I know boundary conditions, is then it mathematically trackable problem? It again is a problem. It's not that simple to solve a partial differential equations, even if you know the boundary conditions. Only in case of very simple boundary conditions like spherical symmetry, cylindrical symmetry, Cartesian symmetry, you may find a way of what's called as separation of variables as a tool to solve this equation. If it does not have this source term, in case source term is there, then you will have to use Green's function method. So handling, what I mean to say is that the handling this in this differential equation is not that simple, not that easy, and you might actually have to, in some cases, and what we do is we transform, we use integral transform, we use integral transforms to convert this equation into some algebraic form and then solve that algebraic equation and then convert back transform and then try to find what is meaningful for us. And there are other methods like numerical methods, and where you try to work through the differences, right, forward and backward differences, and you try to solve such differential equations. So the simple idea is that solving this equation is still now further challenging. But do we need, say, information about the curl of this electric field? Say curl is 0, would that help us? Yes, of course. In case of electrostatics, when the curl is 0, that helps us to develop the equation in the form of a potential. We'll talk about that later. So this is our Maxwell's first equation. Also, what do you see in this equation? This equation is linear. It's linear. There are no higher powers of E. So it will allow the superposition. It will allow that if there are two solutions, the sum would also be a kind of solution. Then also it is non-homogeneous because there is charge density. See, there is charge density because of which it is a linear non-homogeneous equation. So keep these ideas in mind, and they're very useful about what symmetry it has. I will talk about the symmetries of Maxwell's equations in detail later on. So right now, this is what is Maxwell's first equation. What is Maxwell's first equation now? It is that divergence of the electric field is related with the charge density divided by epsilon naught. Now you may say if the charge density is 0, right, then what it boils down to, so suppose charge density is 0, then divergence of electric field is 0. So is it that charge density is 0, electric field is 0 all the time? No, that is not the case. There could be regions where charge density is 0, right? But the electric field still has a profile. For example, I have some sheet which is charged, because of which there will be electric field, right? So suppose this is a sheet, there is a sheet which is charged, right? The sheet is charged. Now there will be an electric field due to this sheet. Fine. So electric field will be changing from point to point. Say if it is a finite sheet, it will be changing. Don't think of an infinite sheet and electric field as a constant magnitude. No. Suppose now it is a finite sheet, or take a sphere or whatever. So what the charge is here, it's not here. So in this region there is no charge, but the electric field has a profile there. So charge density 0 does not mean electric field is 0. No. It may be that you don't have electric charge and you have electric field 0. That's one possible solution. But even if you don't have charge, and you still can have electric field, right? You can have charge somewhere and there may not be charge everywhere. And in the regions where there is no charge, electric field will still have a profile. Now somebody misinterpret again this equation as now divergence of electric field is 0, and it means that, right, the differentiation of electric field is 0, therefore electric field is constant. That's also wrong. That's also wrong understanding. Divergence of equal to 0 does not mean electric field is constant. It is divergence. It's not like a differential operator in one variable. What divergence gives you? Remember, what did I say what divergence gives you? It gives you how field spreads out, or how field shrinks. Field may not spread out or shrink, but it still will have a profile. For example, I have a dipole, right? Now I have a dipole, there is a positive charge here, negative charge here. Lines of field will come from the positive charge and go to the negative charge, right? The divergence would be 0 because there are two poles, right? So, right, the divergence would be 0 if I construct a surface around them, because the net charge inside is 0. But that does not mean that electric field is constant, because you see the electric field has a profile. It is coming, the lines of force are coming from the positive and sinking to negative, and the direction of the electric field and magnitude is changing at every point. Remember the electric field due to a dipole. So that means electric field is not constant. But what electric field is not doing, it is not spreading out, or nor it is shrinking. So that is what divergence means. If the divergence is 0, it simply means that the field is neither diverging nor shrinking, but it does not mean that field is constant. So field is constant is something else, right? See, field is constant, it is not contained in that divergence is 0. Divergence is 0, what is guaranteed is that the field is not spreading out nor shrinking. So this is a confusion that most of the students have. That's why I try to clarify it. Now we go to the next important equation, and the second Maxwell's equation. So first, second Maxwell's equation, the first two are about electric field, the second two are about magnetic field. We'll go to the next equation, which is equation about electric field only. And this time, electric field is related with not to the source of charges, but to the changing magnetic fields. So there was an observation by Faraday, Michael Faraday, and this is a very interesting observation, which is called Faraday's law, and you need to understand this very thoroughly. And so you see, suppose I have a region, I have a metallic wire. Simply I take a metallic wire, and I have a magnet, and I have a north and south pole of this magnet, and I move this magnet up and down, right? So what I am doing, I am moving the magnet up and down, is that I am changing the magnetic flux through this surface, right? I'm changing magnetic flux. And what Faraday found experimentally, that the current is induced in the wire, that current will flow. Of course, the direction of the current will change. As I move in, it will be in one direction. When I move out, it will be, so it will be kind of an AC current that would be generated in this coil, right? Or fluctuating current that would be generated in this coil. What Faraday found was that E, the electric field, the EMF, we'll write it in terms of EMF. The EMF is in the induced in the coil is minus rate of change of magnetic flux, right? Magnetic flux, how much magnetic flux is changing through this wire, through this surface, right? Now I put it in this equation in the integral form. So you know that E can be put in the integral form because E is kind of voltage, so it is like work done. So here the work done on the charge is over the we take the entire path. So we use this whole path, we integrate E dot dl. E is the electric field which is created by the change in magnetic field, is minus del by del t of integral of this is flux by definition is B dot ds over this surface. This surface is not a closed surface, keep that in mind. It's an open surface. Fine. So how much work is done on a charge along the entire loop, right? So that is the EMF. So per unit charge is EMF, and that I can write this way, right? I just write work done over the small step, and then I over the small path, then I integrate over the entire ring, and that is this integral. And flux through this surface is what? Integral of B dot ds over the whole surface, this surface that I am considering. Remember, this is a flat surface and this is an open integral. It's not the Gaussian surface, right? Keep that in mind, because we know that magnetic flux through Gaussian surface is always zero, because we don't have magnetic monopoles. So it's an open surface, no confusion about that. Okay, but now you have a surface integral on this side. On this side you have a surface integral. On this side you have a line integral. Now look for a theorem that will connect, say, surface integral to line integral, or line integral to surface integral. So I will use the theorem of curls. What does that theorem tell me? It tells me curl of an electric field, curl of any vector over a surface is equal to, over a surface, or the bound surface is equal to the path integral of that field over the boundary. All right, so now I know this is the boundary, this is the boundary, this dl, no, this integral is a boundary integral, so I convert it into surface integral using what? Using the theorem of curls. This is also called Stokes theorem, remember that. It's also called Stokes theorem. Okay, so we invoke Stokes theorem, and what do we have? Come on, what do we have? We'll have integral over the boundary. That will be, now this already over the boundary, this is over the boundary, now over the this is over the surface, so it will be curl of E dot dl dot ds now over the surface is equal to minus del by del t of B dot ds. This is the same surface. Now we have again on either side we have the same integrals, right? Therefore the integrands must be equal. This equation is only meaningful when the integrands are equal. So once I match integrands, what do I get? Come on, once I match integrands, I get curl of E is equal to minus del B by del T. Now you will say, okay, so we have electric field is curling, it's curving around, it is circulating, and the source of that electric field, but we know that electric field due to a static charge never curls, it doesn't curve around. Like we have a bunch of charges, the electric field always either comes out or goes in, it doesn't curl, right? For electrostatic field the curl is zero, but here we are having electric field that curves around, it curls around, but this electric field has a different source. It is not the electric field we know from electrostatics. This electric field is created by change in magnetic field. It is not created by a static charge source. And question is, what is electric field curling around? It is curling around the change in magnetic field. That's very important. So you look at this diagram. So what is electric field curling around? So electric field is curling around. This magnetic field is changing in this region. So magnetic field is changing this way. Electric field is curling around that change in magnetic field, right? So this electric field, which has a finite curl, and that curl depends on how much magnetic field is changing, that electric field is produced at first place by magnetic field. It is not produced by a static charge. And the profile of this electric field is a different. And how do we get the profile? How does the electric field change from point to point in space? It is obtained by taking the curl. If I know how the magnetic field varies in time, right? I know the time derivative of magnetic field. I would be able to calculate what is the electric field, what is the profile of the electric field around this changing magnetic field. And in case that a magnetic field does not depend on time, it is zero, then of course you have curl of electric field is zero. So when you have two equations, curl of electric field equal to zero and the divergence of the electric field is rho by epsilon naught, then these two equations is nothing but the entire electrostatics. If you say that study of electrostatics is the study of the first two Maxwell's equations and keeping magnetic field time independent, then you're right. So the entire electrostatics actually boils down to these two differential equations. But are they simple to solve? Not that simple. I still tell you, they're not that simple to solve. There would be challenges in solving them. In fact, this curl of equal to zero, it provides an extra input. That input is that I can put now E in the form of some potential and the problem becomes more trackable. You can get what's called as Poisson equation and Laplace equation and then look for their solutions. And that's typically what we do by using those methods of separation of variables, and all that stuff will come later on. So is that now this clear? So we have two Maxwell's equations now at place. With the first Maxwell equation is nothing but the differential form of the Gauss law. It tells us the divergence of the electric field is rho by epsilon naught. The second equation that we obtain is nothing but Faraday's law in the differential form. And again, why do we need differential form? Because we want to see the profile of the field. We want to see how the field varies from point to point. We want to see the functional dependence of the field. That's why we are interested in solving differential equations, and so that is not contained in the original version, right? So now we have the third equation of the Maxwell. We have the third equation, very important, and third equation is very simple to propose because that tells us very simple fact that magnetic fields lines are always closed loops, always closed loops. Doesn't matter what their source is, they're always closed loops, right? And since they are closed loops, the divergence would always be zero, and that divergence of the magnetic field is zero is what is our third Maxwell's equation, or the net flux. You can also propose like Gauss law of magnetism, which is that net flux through a surface would be zero, magnetic flux through any closed surface would be zero. So the idea of proposing it in the same way as earlier two equations would be like that the total magnetic flux over a closed surface is zero, right? So and its differential version is that divergence of the magnetic field is zero. Remember, this is a fundamental rule and there is no exception to it, right? I mean, this is there. This is an experimental fact. Why it should be zero? Why not non-zero? Why don't we have magnetic monopoles? That we don't have. That is the problem. If we have them, we'll not violate any law of physics. In fact, Maxwell's equations will look more beautiful if there would be magnetic monopoles. That's why people try to look for magnetic monopoles. But this equation is nothing but an experimental fact that experimentally we don't have monopoles, and experimentally we don't have magnetic lines of force spreading or shrinking. They only go in closed loops, and the fact, since they always start from one point and terminate at the same point, is simply that doesn't matter how you choose a Gaussian surface, the net flux through that would always be zero, and its differential version is that divergence of the magnetic field is zero. That's what it translates to. So now we have three equations at place. So what are those three equations? Let me write down. The first equation, the divergence of the electric field is charge density divided by epsilon naught. The second equation, curl of electric field, is equal to the time rate change of magnetic field. It depends on how magnetic field changes in time. The third equation, that there are no magnetic monopoles, the divergence of the magnetic field is zero. Now the real job is fourth equation, and that's where the whole contribution of Maxwell comes in. Now, what's fourth equation? What have we left so far? The law from laws of electromagnetism. We just write down Ampere's law and try to write down its differential form. So what's Ampere's law? Ampere's law is that the loop integral of a magnetic field is nothing but mu naught if you are in vacuum and current enclosed, right? This is experimentally verified. This is experimentally established fact that you're right in terms of what's called as Ampere's law. You can experimentally test it. It's not something that cannot be tested, right? So now I can write down the same equation as we proceed in the similar way. So I can write down B dot dl, the left hand side, the way as it is, mu naught, and I put this I in the form of a distribution, current density through the surface, or flux of current density. So the flux of the current density is what will quantify current through a surface, right? Suppose I have a surface, I want to see how much current is flowing through that surface, and that is given by current density, current by area, and the total flux of the current density measures the current through this surface, will measure the current. Now I can convert this into surface integral. This is the surface integral, so I can convert this into surface integral again by using that Stokes theorem. So I can write curl of B over the surface that is bound by the loop, over the surface bound by the loop, equal to mu naught integral J dot ds. And again, the same argument, the integrals are over the same surface you choose, and therefore the integrands must be equal. So if that logic goes, and then we have curl of B is equal to mu naught J. And what is this? This is the differential form of Ampere's law, and we should be happy we are done. Now we know the magnetic profile of the magnetic field will depend on the current density. If I know the current density, I will tell you what the profile of the magnetic field is, right? And even if I don't know the current density, I can still find the profile of the magnetic field if I know the boundary conditions, right? Now the question is, there is something terribly wrong with this equation. Something is terribly wrong with this equation. What is that thing? I take divergence on both sides of this equation. If we take divergence on both sides of this equation, then what do we get? We get divergence of curl of B is equal to mu naught divergence of J. So far, so fine. Now look at left hand side. Look at left hand side. Divergence of curl, that is by vector identity itself, and that is 0, always 0, or you calculate it, it will always be 0, or by intuition that magnetic field is curling around, it's not spreading out. So by our way of understanding divergence and curl, the left hand is 0 anyway. But what about right hand? It's not always 0. That's the problem. If you look at the first equation that we derived today was the conservation of charge equation. That tells me del dot J is equal to minus del rho by del T. Aha, so that means this side, the right hand side, is not always 0. It could be del rho by del T. So therefore, there is trouble with this equation. There is something fundamentally wrong here. Something is missing. Some piece of information is missing, and we need to fix that. But remember, what was rho related to in our first equation? It was related to electric field. So with that in mind, could we modify this equation that it takes care of the conservation of charge? So that was the aim of Maxwell, to restore the conservation of charge in the fourth equation. So if I can restore that conservation of charge in the fourth equation, I may find some deeper hidden secrets of nature. That's what he did. So what we do is that we add a term to it. Let's add a term to it. So let me add a term to it. So what is that term? So I will rewrite the Maxwell's equation. Del cross B is mu naught J. Let us write this term. Let's add this term. And then we'll justify why we added this term. Now take again the divergence on both sides. That would be 0, right? So we'll have, if I take divergence on both sides, So left hand side would be divergence of curl, which would be 0, which means mu naught. I can take mu naught out. So divergence of J plus epsilon naught del by del T divergence of E, that's equal to 0. But mu naught is not 0 because there's a constant. Now, what is divergence of E from? Divergence of E from the first equation is rho, right? By epsilon naught. That epsilon naught and this epsilon naught will cancel. So what do we have? Divergence of J, come on, plus epsilon naught del by del T. And I use first equation, which is rho by epsilon naught equal to 0. This epsilon naught and this epsilon naught will cancel. So what do we have? We have del dot J plus del rho by del T. And that is 0 because that is conservation of charge. So the left hand is 0, right hand is also 0. So this not only makes your left hand equal to right hand, this term, but it also rescues the conservation of charge. And therefore we are done. We have written a we have modified Ampere's law. We have modified Ampere's law. We should be happy that we have added a term to it and rescued the conservation of charge. That's okay, but is it what there's something, I mean, you can ask a question, something is terrible, that you said that I wrote the Ampere's law by experimental observation, right? And now you are putting error in it, in the experiment. You are putting some term. And what happens to our experimental finding? Our theory cannot go against the experiment, not at all. So this is very interesting. Come on. So now I have my modified Ampere's law in differential form, which I call the Maxwell's fourth equation, is mu naught J plus mu naught epsilon naught del E by del T. Right. Now you'll say, okay, this term was not there, and we experimentally found only this much. When you put this term, your experimental result is wrong. But there is the catch. This epsilon naught mu naught, it makes the difference. Actually, when you calculate this epsilon naught mu naught, it is actually 1 by c square, where c is the velocity of light, is mu naught epsilon naught. And remember that is 1 by 9 into 10 to the power plus 16, which is 1 by 9 into 10 to the power minus 16, because the velocity of light is 3 into 10 to the power 8. So in your system of units, that is the SI system of units which you use in laboratory, this is the correction term is extremely small. So small that in ordinary experiments that Ampere carried, you can never see this correction. So because the correction term is small. Now you'll say, okay, it's a very, very, very small correction. How it is going to change the world? It changed the world. It changed the world, because small correction does not mean it will have a small effect. It has a huge impact. It creates new field of study. It tells us that now these electromagnetic fields can survive independent of charge and currents, and they can create a kind of a wave, a kind of jigglings in space-time called electromagnetic waves, which travel of their own. They have energy, they have momentum, and then guess what? We understand optics is nothing but obtained by just this small correction. It gives rise to entire field of optics. You extract it from electromagnetism. So that is the beauty. So that is very important. Also remember, this is our current, right? So this is our current. This is our current, real physical current J, and this is also current, and we call this as displacement current. So magnetic field is created not by physical currents, but by changing electric fields also, right? Electric field was created by changing magnetic field also. So magnetic field will have a profile. It can have a profile. It will change from point to point, not only by a physical current will create it, but there would be, if there is a region where electric field is changing, magnetic field can be created, right? So now we have a scenario where electromagnetic field changing creates an electric field which is changing. That electric field is changing, can now give rise to magnetic field even if there is no current, and that magnetic field would give rise to electric field. Each change is actually curling. Each type you create a field, a magnetic electric field, it curls around the source that creates it. This way the electromagnetic wave is generated and it travels through the space. And in a plane wave consideration, you can easily figure out that the electric field and magnetic field, they are perpendicular to each other, and they are perpendicular to the direction of propagation. That we can actually prove through these equations. And so now I rewrite these four equations directly and summarize our today's lecture. So let's write down all the four equations now. For Maxwell's equations, the first equation is that divergence of electric field is charge density divided by epsilon naught. The second equation is curl of electric field is the rate at which the magnetic field changes. The third equation is that we do not find magnetic monopoles, that divergence of the magnetic field is 0. And the fourth equation is that magnetic field has a profile that depends on the physical currents, plus it will depend on if the electric field is changing with time. These are the four equations. Now let's inspect these four equations and a bit discussion before I close today's lecture. Now, what do you see in these four equations? There are, this is a homogeneous equation, is a linear equation. Homogeneous because there is no source term, right? This is inhomogeneous because there is a source term, but it's a linear equation. This is also a linear equation because single powers of E and single order derivatives, so first order linear differential equation. This is also homogeneous because there are no source terms, and here is a source term, so this is inhomogeneous linear equation, right? So first of all, let's just get a feel of what kind of equations are them or these. Now all these equations have some beautiful symmetries, and that is what we are going to talk in our next lecture. I will focus on the symmetries of Maxwell's equations, and then we will derive the equation for electromagnetic wave, and then of course we will get into the conservation of the energy of electromagnetic wave through a very interesting theorem called Poynting theorem. We'll also discuss third law in Newton's third law in the light of electromagnetic phenomena. Let's, if there are moving charges, how we need to look at the third law of motion. Thank you very much. I hope that I made some sense and this lecture was absorbing, enjoying. Please do share comments and tell me that whether you like or dislike it, and tell me, you can also comment on how to improve the quality of these lectures. And thank you very much. Thank you for engaging.